this section on like Python data structures. Um, so you can just see like what we'll get into next is. Give me 1 second. So we'll get into trees. We'll probably wrap this up. I'll try it one way or the other, which we'll like move on from this week, um, and then we can get into like back to some SQL stuff. I also do want to mix in um, some of the stuff on like working with different databases. Like Snowflake, BigQuery, PySpark, like that material. I think that it will come up, and then we obviously have like just tons of additional interview questions to go through. But I think that maybe we will, after doing a little bit of SQL stuff, try to move, just like make sure we cover, right? Like we never got to like Snowflake or Redshift or things like that. So just like how those components work under the hood. As for so like I said, we'll get into trees. It's kind of like building off of linked lists. For me, like I'm making these contributions to this, to this AI code base that kind of code that does actually generates code, and a lot of the stuff that actually I'm coming across is working with like trees, and really it's like graphs, and trees are just like a type of graph, and honestly, so are kind of like linked lists. Really, like with all these things, you can think of like a graph. It's really just like consists of nodes and then pointers, right, to like the next node. And with a linked list, well, you just have a single node that only has kind of like one node attached to it, right? I mean, you could actually have it reversed, right? But there's really just one kind of equivalent. Like there's this one arrow is going, just to point to like a single node. With a tree, we could have, well, this node actually points to like two sibling nodes, right? And with a graph, you may think that with a tree, maybe we have this idea of like levels, right? But with a graph, it's very, very similar to trees. We can just have these nodes, point to multiple, like also not only point down, but also point like across. Okay, so this node here might have a sibling that it directly points to. That would be like as well as child nodes, right? Whereas with a tree, which we'll get into, we have this node really just has child nodes, and these two nodes are only connected really through their parent node. Okay, so but you can start to see how each one of these data structures really consists of like these fundamental elements, which is nodes and basically edges, right? Where the edge is the link between each node. All right. So like even with a linked list, like we have like one, and then the next element is two, and then we have 5, right? Each one of these is a node, and then the pointer is like an edge in between each of the nodes. Cool. So just to review linked lists, I think that I did not deploy one of the labs. So we can, after the lecture, you can move through that. But just to go through linked lists, just remember like the implementation is really just consists of two different classes, right? It's the linked list itself, and then it's an individual node. And you can see, right, like the only attribute we really have to keep track of is like the value, and then what comes next, right? Where like this next node thing is kind of like, right, like the edge in between it. All right, so now let's say that we can just quickly create our list. I think the lab has you move through that, but let's say we want to do like reversing a linked list. So let's just review that for a little bit. So just remember how this works. Like I typically would draw it out, so it'd be like 0 points to 1, 1 points to 2, and then currently 2 points to like none, I guess. But it's like this, 0, 1, 2. And then if I reverse a linked list, the first step I would do is I like to add this none node, like this right? And then it's really 1, it's going to be like, 1 points to 0. So instead of 1 pointing to 2, 1 will point to 0, right? So we're switching this so that a node really is going to point to the previous node, and 0 is going to point to none, right? And then 2 is going to point to 1. All right. So for each node, essentially, we're going to have it, you can start to write this out. For each node, have it point to the previous node, right? The previous node. All right. So then we can, we can start to like code this out. So def reverse a linked list. And what we want to do is, for each node, it's really like, we have to start kind of somewhere. So we'll call this our current node. And that'll just be the first node. That'll be my linked list.head. Let me just make sure the way this is, right? So linked list has this attribute of head. And that will just point to, right, the first node. And then remember, like, the main thing we're going to want to do is have current node dot the next, I call it next node. We want that to point to the previous, okay? And we also know we're going to want to do this for each, like, kind of increment, right? Move through each one of these nodes. But this is the main kind of step, right? Is that we're switching this, right? We're having each node, instead of pointing to the next one, it points to the previous one. And now we kind of like need to obviously define this. So what's previous? Previous can start, right, at the beginning at none, right? So if I start at 0, this is my head. Previous can start at none. So previous equals none. Okay? And then we can say while there's a current node, we can kind of do the main kind of processing operation, which is to, right, set the current node to previous. So if this is 0, right, we set it equal to none, right? And then what the next thing we want to do is like increment. Okay? So to increment, let's think about what we want to do. So we want to increment the current node to be the next node. So the current node equals the next node. This is not right defined, right? I can't do current node.next because we reassigned it. So we have to fix this. So the current node equals the next node. So up top here, I'm going to have to do next node equals current node.next node. Okay, so we're like capturing it before we then change it. So the current node equals next. And then we also need to, have this previous, right? So the previous has to equal current, and that better happen before this occurs, right? Before we increment this. So we need to say that previous equals current node, and then current node equals the next node. So let's just think about this again. So basically what we're doing is we're going in this direction, and we want to, for each of these pointers, have it go the other way. So if we're on 0, we want it to point to previous. So current node.next node equals the previous one, this guy, right? And then we want to like increment. So the previous node is going to be my current, right? So we're incrementing. So now we're up here, previous equals 0. And then the current equals the next node. So, right, that's the current is going to be 1. And then that's basically it. And we just need to capture this. We need to capture the previous. We need to capture what that next node is before we change it. Okay, so that's what we did up top here. All right, and like I said, this is kind of the order that I do things. I like do the main operation first, and then I just fill in the rest of the gaps afterwards. And then finally, we can we want to change the linked list.head. Linked list.head equals to, and think about when this will end. This is going to end when the current node is none, right? Eventually, current node is going to be the next node, and we're going to get to like 0, 1, 2, back to none, right? This next node is going to be none. This is going to exit, right? And so we're going to want to say, okay, ll.head is now not the current node, right? Because this is going to be none, but the previous one, okay? Which would be right here, too. Let's see. I don't, and like, certainly I get this wrong sometimes. So we'll just try this. So we previously had this, right? 0, 1, 2, none. And now after reversing it, 2, 1, 0, right? So we are moving backwards. The other thing for me, like I just remember like with some of these operations, right, we kind of have like two options here, it seems like. Either you kind of stop when the current node is none, or you can do like stop when current node dot next is none, right? We saw that was helpful sometimes. Like this actually, so I tried this like before class and this broke. And just remember, like the way that you can debug this, of course, is for me, just print out what like the current node is. So you can always debug this stuff, obviously. If you get this in an interview, etc., you can debug it, and it's also fine, right? So if we reverse again, just define it. Oh, sorry, and we should probably do current node.val, right? So you can, it just helps to debug to make sure you're incrementing stuff properly. So it's fine to do this when you're coding it in an interview, and it's also very fine, in fact, I'd say like preferable, to lay out your logic, all right? That way the interviewer can like follow along with you and help you out, right? Like they'll typically just take it as a syntax error or like a mental, quick like mental mistake, that you can easily fix if you lay out your logic first. All right, so either way, just lay out your logic, especially if this is like a video call or something like that, and they'll be able to follow along with you. All right, cool. All right, next thing, we're going to move into trees. Before we do that, okay, so we can kind of move through like a couple data structures, and then we can cover like breadth first search, and depth first search. So, so this is a tree. This is an example of a tree. And basically, like, you can kind of see the way that we're going to represent it. So we'll have like this root node, we could just say like is 6. So with a tree, we have, just describing them, each one of these is called a node, right? The edges are the links between the nodes, right? And then this node is kind of special. It's called the root node. It has one child, right, which is like the direct link. This node 9 has 2 children. And then if a node has no children, it's described as a leaf node. So what are the leaf nodes here? Right, this is a leaf node and this is a leaf node, right? Because both of these have no children. If you think of the depth of the tree, typically the depth of the tree is described as like, you can think of it as like the maximum depth. So these are the different levels, level 1, level 2, level 3. The depth here is 4, right? Because you have to go down 4 levels kind of before you reach the end. All right. Okay, so we can say, okay, this is our root node, is 6. And then if we're going to describe the tree, you can do so. There are different ways, but like kind of a basic way to do so is just using a dictionary. So you can say 6, and then here you can put in the list of children. So 6 points to like 9, right? And then 9 here points to 12 and 11. So you can kind of see how you traverse the tree, right? 6, we describe the root node, so we know we have to start here at this key, and then from this key we are putting in the children, right? So this has one child, 9, and then we go to this child 9, node 9 has 2 children, 12 and 11, and then you would have, of course, the next one, 11, and that has one child, right, which is 3. So this describes the tree, right, like perfectly. All right. And you can see that's just what I did here. this is one data structure, right? Is trees. We'll go into like how to move through the various nodes of a tree using breadth first search and depth first search. But before we get in there, there's two other data structures to quickly cover. One is stacks and one is queues. So stacks, the way you can imagine it is stacks are just like lists. I mean, so are queues. But the way it all really depends on like how we add and remove elements to these lists. Okay, so with a stack, let's say we have the elements 3, 4, and 5, that we're going to add. You can imagine it's kind of like this. Like first you put on, it's like, think of it like Jenga blocks. Like first we put down the 3 block, right? Then we put down the 4 block. Then we put down the 5 block. And now we're about to remove things from the stack. So when we remove the first block, it's going to be 5. So 5 is the first guy to go. Then the 4. Then the 3. Okay? So in other words, with stacks, it's the first in is the last out, right? We added 3 first, then we added 4 first, and we added 5, right? And then when we removed it, it was 5, 4, 3. So the first guy in was the last to leave, okay? And that's a stack. How do you implement a stack in Python? It's very easy, right? All you can see what I'm doing here is I just have a list. I add in 3, I add in 4, I add in 5, right? 3 was the first to enter, followed by 4, followed by 5. And remember, if we want this is the last guy to enter, we want it to be the first to leave. We should all know how do we do this, right? Just pop it, okay? So this is a valid stack. So for a stack in Python, you don't have to do anything special. You just literally create a list, add, right? Then just remove from the end, right? Stack.pop, 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 5, 4, 3. All right, now queues are like, whenever I think of a queue, I just think of literally like people lining up in a bank queue. All right, so for a queue, it's not, you don't want to use pop here, right? Because 3 enters first, 4 enters next, then 5 enters. So if we use pop, right, it's not equitable, right? Like that's not fair. We want to have 3 be the first person to leave. Now the issue with this, right, you can use Python obviously, right, to do this because you can do pop, I think at index 0. I forget if this takes a keyword argument. Maybe we just do the index, right? Pop at index 0, you can do that. But right, the issue with this is just remember what this means is, because we know the way that lists work, right? If this is at space 100 and then this is at space 106 and this is at space 112, everyone has to move down. When we moved this 3, just that one pop has a cost of n, right? Because 4 and 5 both had to move their location down 1, all right? So we don't want to use a normal list, right, when we're removing from the front. So just remember that, right? With lists, operations at the front of a list cost you n. So either adding to the front of a list, removing from the front of the list. With a queue, we're removing from the front of the list. We don't want to do it. So instead, we use this collection deck. And I looked up before, like, how do you pronounce it? And it is just pronounced deck. I was hoping maybe was it pronounced like DQ, which would make more sense. But I do think this is called it is like a double. I forget, this double entry queue or something like that. Like it does come from that word queue. Like the idea is that you're able to remove or add from either side. Does someone know it? Double-ended. Thanks, Conwell. Double-ended queue. All right. So you can still think like when you use a queue, right? You need to use this, right? Double-ended queue. You should be using this double-ended queue attribute. So, okay, so we create a queue, and we just do the same thing, queue. I think I can do append. Let's try it. Yeah, so we can do queue.append, queue.append2, queue.append3, and now if we, okay, it just has a return value of it, but if I look at queue, right, it has 1, 2, 3, and now you just do, instead of pop, you can see we already have it, pop left. All right, so remove from the left side. So 1 was the first to enter, 1 should be the first to leave, just like in a bank. All right. So just remember that, right? Stacks, kind of normal with lists, add, just append, and then pop, leave from the end. They're kind of like those Jenga blocks. And then with queue, it's like I always just think bank queue, right? And we use this double-ended queue object because we don't want to have that, because we're performing operations at the beginning and end of a data structure of the list, which we don't want to do. So instead we use this because it makes it more performant. I think there were a couple questions. Yes, first in, first. Thank you, Wayne, for that. So queue, right, first in, first out, right? Kind of like unequitable, the way I kind of think about it, right? Queue first in, first out is equitable. Yeah, and then stack first, last in, first out. Yeah, very good. All right, so now we can move through like depth first search. So with depth first search, what we do, the kind of whole approach is that we're basically going to like, it's almost like splunking or something. Like you just like probe down from the root node to the leaf node, okay? And then we would explore this guy, this next one. Then we go down the next path. And we'll go from root node down to the leaf node and then explore this one, right? But we're not, right, that's very different than what we'll see next, which is like breadth first search, which would be exploring in levels. Like first 6, then 8, 9, then 4, 7, 12, 11, then 3. That's breadth first search. With depth first search, it's like probing down, right? From the top all the way down to a path, then down to another path, then down. It could be this one, and then down. So it's one path from root node to leaf node at a time. And the way that you implement depth first search is with a stack. Okay, so we'll kind of see that. So basically, the idea, and the reason why is because a stack, as you'll see, will like have this property that it allows us to like keep digging, basically. So the approach is going to be that you visit. We'll start with the root node. So you visit the root node, and let's say we create a stack, and that'll be like 6, okay? And then we visit the children, okay? And that'll be like 8 and 9. All right, so it'll be like, or we can do this. We'll say, have this stack. We can say process it, and then visit children. So we'll create a stack, and we'll see how to code this in a little bit. But for now, let's just understand the approach. So have the 6. You can imagine processing is just like printing the number 6 for now. And then we'll visit the children, right, which will be 8 and 9. So now we add 8 and 9 to the stack. We've already processed the 6. Like when we process it, you can kind of remove it. And now what's the next element to process? So it would be first in, last out. It would actually be this 9, right? So it's the guy at the end, right, that we're going to be handling. So we print our 9, and then we visit the children of 9. So now it's 12 and 11. Okay? And then we're using a stack. Why is my... so what's the next thing to process? The guy at the end, right? This 11. So now we remove the 11 because we process it. You can imagine printing it. And then what's the add visit the children of 11? So that would be 3, right? And then what's the next one to process? This 3. So then we print 3, visit the children. There are no children, right? And then go to the next thing in the stack. What's the next thing in the stack? The 12. So we remove it, process it, meaning like we print 12, visit the children. There are no children. So then what's next is the 9. We would add this. We would also keep. I kind of didn't get into this. You also do keep track of like the visited nodes. So these things would already be visited. So you don't process that. So then what's next is 8. Okay. Right, because 9 I think 9 had already been handled. And then we would process 8. I mean, we print out 8. Visit the children. So 8's removed. 4 and 7. Okay, then we print out 7, then we print out 4, and then we're done. Okay, so basically we have this, approach of, because we're using the stack, right, where we're like always just taking things from the end, it just allows us to, okay, we 6, 8, 9, visit the children, last guy is 9, process 9, visit the children, 12, 11, right, last person is 11, process 11, visit the children, 3. So it has this approach of, because we're using a stack, that we basically keep digging. Right. Let me see if I can plug this in. Any questions about that before we implement this? All right, so that's the main thing I always remember. Like, I just try to remember is like, all right, I'm working with a depth first search. This like keep digging approach means that I'm working with a stack. So now, how do we implement it? Well, first of all, we need to represent this graph. I think I'm using, we'll just use a subset for now. So it'll be def DFS, and we want probably like for each of these, you're going to do the root node and the entire tree, right? And let's just do pass for now. Let me make sure I'm plugging in. Unplug my. There you go. All right. So DFS, root node, and the tree. And now we do the tree. And the tree is going to be, let's see, 6 points to 9. That's it, actually. 9 points to 12 and 11. All right. And then we want 3, and I think that's it, actually. And then 3 points to nothing, actually. Right? 6 points to 9, 9 points to 12 and 11. Oh, and we could also do 12 too, right? 12 points to nothing too. Right? And then 3 points to nothing.
11 points to 3.
11 points to 3, thank you. I don't even think we need... I'm pretty sure we don't really even need these. All right. So now the next thing we can do is, implement, this. So our root node equals 6, right? And now think about what we want to do. So we want to, first of all, declare a stack, okay? And this stack should have our root node, okay? And then we'll say, like, while there's a stack, like, while we still have elements in our stack, we want to perform an operation. Okay, so that operation is like process the node, the current node, and then basically like visit the children, adding to the stack. So what's the current node? The current node, just remember, like, as you add to this thing, you need to remove it from the end if it's a stack, right? So it's okay. While there's a stack, we're going to say the current node equals stack.pop, and that's probably like that's the part I always mess up. Is right. We're removing from the end with a stack, and then so we can print the current node. We can also print the stack. So we can just say current node, and then just for debugging purposes, the stack. Okay? And now the next thing we want to do is add each of the children to the stack. So how do you do that? Basically, to get the children, we can do tree. Now, if you do tree, just access, right, the current node, that's pretty good because it does, right? 6 would give us 9, you know, and then we can just add the children to it. But the issue is going to be like when we get to 3, right? It's going to give us a key error. So instead, what I like to do is, and what everyone probably does, is tree.get current node, and then we can always return a list, you know. And this would be like for child in tree.get current node. So, and then I'll just finish it for now. It will be stack.append child. All right, and we'll just, this is essentially it. So let's think about it. So we start with 6 as a root node. All right, we're going to remove 6 from the stack, right? Remove it from the end. We're going to, so now we're working with 6. Our stack is essentially empty at this point. Then we go through all the children, which we do by tree.get current node. So tree.get 6 gives us back 9. We add 9 to the stack. Okay. Then our stack has 9 in it because we've added it. So our stack has 9. We go through, that's the current node. Our stack, once we remove it, is empty, I guess. And then we can go through each of the children, right? Tree.get 9, that gives us 12 and 11, right? And then from 11, then we add 11 to the stack, 12 and 11, we remove from the end, right? Which will tree.get, which will then add this 3. Let me operate it. Let's execute it, and then I think it will also kind of make sense. I want to move this print just so you see the stack before we remove the element from it. I just wanted to move it up 1. Okay, so you can see we start with 6. Our stack begins with just 6 in there. Remove it, right? The current node is 6. Then we go from 6 to 9. So we add in the 9. Then we go from 9, and I'll take this part slower. So we remove the 9, right? Stack is 9. And we do add in these elements, 12 and 11, right? So now our stack is 12 and 11, right? 12 and 11. The key, so you can see that the next thing we do is we add, 11 will become our current node, and we'll add in 3. So before we process 12, we're going to process 3, I think, right? So it's 12 and 11. You see that? And then 11 becomes the current node because we do stack.pop. And then we go through 11's children, which is 3. And then 3 gets processed, right? And then 12, right? Before 12 does. So that's kind of, for me, like confirming that this is depth first search is working. I'll just pause and let you all kind of like look through this for a second. So again, like the main thing that you're doing is you're just visiting these nodes in order of the stack, right? And the way that you're adding to the stack is we're kind of getting our current node by removing from the end of the stack, which you always do, and then we're visiting the children of the current node, okay? So because of that, you kind of just want to, this is my stack, visit the child. Now this consists of my stack, visit the children. 12 and 11 consists of the stack, visit the children of 11. 3 consists of the stack, right? Add 3 here, process the 3. 11 has been processed. Then finally we get back to 12. You can see that 12 and 11, process 11. Add in, right, this child of 3, and then after processing 3, then you go back to 12. The only kind of edge case is what we saw before, that you can like revisit. You don't want to like revisit nodes, so you can add in just like a set. Normally you do like visited equals set, just create a set, and then while stack current node, you can just, if it's the current node, you just say that, okay, I've already visited it. So it'd be like visited.add current node, and then we can say basically only process this if current, if current node not in visited. Yeah, so you basically just put an if statement here. So it's like, basically you're saying, if you just think about like what you don't want to do again, I don't want to reprocess, right? Reprocess a node I've already processed, okay? So that's what this is, unless I'm possible I messed it up, but I think I'm okay. So we have this set of visited, and then if my node, if kind of my node is not in visited, then we're okay to kind of process it and append its children. Otherwise, you just remove it, basically. You just skip it. Let's see if there's a question here. When will the edge case search erase it? Okay. Yeah, when will the edge case? I do have an example of this. This is a typical example, right? Where there's a cycle in this graph, So it's like if you get to H, you can imagine kind of digging through this, getting to G, right? And then this also would have G, and then this also would point to G. So what this would actually result in like an endless loop. So to do that, so you would kind of cut off, right, this endless loop if every time you get to a node that has already been processed, you just skip it, right? You don't repeat it. So this G would only be processed once, and you would just go back up. So it'd be ABDG, ABDG, E, right? I would do E.children, but this would have already been visited, so I wouldn't process it again. Then I would go to CFH, and once I hit G, it would already be processed. I won't print it again. I won't visit its children, so I won't go back up or anything like that, right? So you can see that's what we're doing. We just create a list. This should be a set, but you create a list of visited, and then you just say if the node is not in visited, then simply don't, like I said, I always think of this as like processing it. Then don't process that node. All right. So we'll have you, obviously implement this, but that's the key thing with DFS is that you're working with a stack, and because you're working with a stack, and a stack means that you kind of like handle the last guy that's been added in. It has this effect of, okay, we just saw C, but now we're going to keep digging and see C's child, right? You just keep digging down. And then it's only when you're kind of done with that, then you move back up. All right, so let's do breadth first search. Breadth first search is really the same. It's just instead of a stack, you use a queue. All right, so we have 6. I should visit, let's just do this, 8 and 9. 8 has children of 4 and 7. And then 9 has children of 12 and 11. And 11 has children of 3. I think we're good. Okay? And here we'll use a queue. So remember with a queue, it's like a bank queue, right? It's equitable. So we visit the 6 that has children. So it's like, visit the 6 that has children of 8 and 9. And then what do we visit next? We visit 8, right? You can kind of see it. So we'll print out 8. Add 8's children. So that'll be 4 and 7. right? But instead of, with depth first search, this guy would be handled. We don't do that. We go to 9. Okay? So let's just do that one more time. So you can imagine 6. We process it, meaning print 6, visit the children. So we'll add 8 and 9 to the queue. Then it's equitable, right? So this guy came in first. So we print out 8. He's got processed. We'll remove him. Oh, and we have to add 8's children. Sorry. So that would be 4 and 7. Then we add 9. Then we go to 9, right? Visit 9's children. 12 and 11. Right? And 9 is removed. Then we do 4 and 7. Then we do 4 and 7. They're each printed out and removed. Then we do 12, print them out, remove. 11, print it out, and then do 3, right? Because we visit 11's children. So you can see that this is kind of like this, moving through, right, the levels. Breadth first search can be quite useful. Like you can imagine if you have a graph and you want to move through and you care this order, like these levels really represent something. Like think about LinkedIn, like levels of connection, right? If you want to ask a favor of somebody, and you want to move through this graph, well, who do you want to ask your favors of, right? Like the people that you're most connected to. Another example would be like web pages. Like think about scraping web pages, and each of these represents links between the web page. And you want to think about, okay, I'm going on Wikipedia, I look up something on Walt Disney, and then we want to get to, the Disney Corporation, and then further that is maybe Pixar, etc., and then further than that is Toy Story or something like that, right? Which is kind of what you would think, right? That's kind of, so when these levels really represent, distance, in a hierarchy, right? Applying a breadth first search, the order that you want to visit, or assign importance, right, can be significant, right? Okay, so just in terms of implementing it, like I said, it's pretty similar. So BFS, the root node, let's say the root node equals 6, and the tree. And then what do we want to declare? We want to declare a queue this time, right? And because it's a queue, we want that double-ended queue thing, right? So from collections, import dec, DQE, and we do dec of just a list that has our root node in it, right? And then we want to say basically while we still have things in this queue, what do we want to do? We want to add to the queue. So first we need to kind of get our current node. And what is this going to be? This is now going to be, remember, we're doing this equitable approach. So first in, first out. So we need to remove from the beginning of the list. So it's current node is q.popleft. And this is really the only difference. That's basically it. And now what's next? We'll go through each of the children. For child in q.get, no, not q, sorry, tree.get the current node, comma, empty list. So when we access, if we try to find 3's children, it won't throw an error. It'll just give us an empty list. What do we want to do? We want to add it to the queue. Q.append the child. And we probably should let's print out the current node. And let's also print out the queue. And then just hope. Let's see. So BFS, root node, tree. See, okay, so the current node, it's always going to do this, say this dec thing. So current node is 6, then we have 8 and 9, and basically we want 8 to be coming out next, right? So that's happening. So it's 6, 8, 9. Then we do, so 9 comes next, and then we want this 4 and 7, 8, 9, 4, 7. Right? And then we want 12 and 11, which comes next, and then finally 3. All right? So you can also see this, right? Because we first add 6, our root node, then we add in 6's children, which is 8 and 9. Then we visit 8, right? Q.pop left, visit 8, finds 8's children, tree.get the current node's children, which I guess is 4 and 7. So that's why we then add 4 and 7 here. Then 9 comes next. 9 has children of 12 and 11. So we print out 9, we add in 12 and 11, right? So it's like, that's the result of this like equitable approach, is we're moving in order from who we kind of see first, right? But the really the reason why I can keep both of these in my head at the same time is like what's the difference? Just the fact that one uses a Q and therefore we, remove from the beginning instead of removing from the end. That's the whole difference in this code. And then the same thing, right? We can just have us visited to make sure we don't like revisit, right? If there's cycles. So visited equals set, and then just put an if block. So it would be, if current node, so we do it after we get our current node, if current node not in visited, then skip it, meaning don't process it and don't add the children. And let's just check it again. Yeah, that works fine. So again, like if you come across this stuff, like if someone asks you this, well, like I would like explain the logic first, right? Like move through it, say, or you can ask them too. You can say, hey, do you mind if I, is it okay if I lay out the logic first, or do you just want me to directly implement it, right? And then say, okay, well, with breadth first search, we basically want to approach this in layers, right? And the way, the data structure that will allow us to do that is if we use a queue to determine, the order in which we visit our nodes, right? With depth first search, we want to have this approach of like digging through the paths, through each path from root node to leaf node. And the way that we implement that is to visit our nodes by using a stack, so that the most recent node that we visited is the node that we'll be processing next, right? And that has this approach of keep digging. If someone just like, I think for a lot of interviewers, if you said that would get you like 80%. Like that shows you understand it. And if you make a mistake along the way, they'll be able to help. They'll be able to help you with it. Like they'll be able to, hey, like you just remember what you told me, blah blah. All right. And the other thing to say is like, yeah, like this stuff is good to know for LeetCode, but like I said, like chances are, if you're working with Python, a couple years into you're going to see this stuff, and so just understanding conceptually like how to understand this code, like you'll see these algorithms and just be like, okay, that's breadth first search. This is how I remember how it works. Right? This is one of those topics that's also just useful in your engineering career. All right. And by the way, like I said, it's the same thing. You can imagine breadth first search, right? Like kind of tweaks on it. Like if it's they say, okay, with graphs, how do I do this with a graph? Okay, maybe I want to first, if you like, or search through a graph. Okay, well I want to visit all the children, right? And then and then add the elements to a queue, and then make sure that those children are visited, right? Like these approaches are used not just with trees, but basically, with other, like if you come across like a graph problem as well. Chances are you won't until like, not on LeetCode, you'll come across just these standard things of trees. Cool. All right. So what to do? Go through this linked list operations lab if you haven't already. It's worth reviewing the stuff, right? Like, and then this kind of covers what we talked about: intro to trees, stacks, queues, and trees, depth first search, breadth first search, and then implementing. So I basically just ask you to like practice implementing it, and then, like I said, there are, this LeetCode. Here's like a LeetCode problem we can do next. But basically, I kind of do it for you and then ask you to like re-implement it next. All right. So I try not to force you to think too hard with this stuff. Basically, you're always with these approaches. You're almost always starting with breadth first search or depth first search, and then maybe tweaking it just a little bit. All right, but my approach is like, all right, first I'm just going to implement breadth first search, and then I'm going to like update it to solve the problem a little bit. Cool. All right, let me